Welcome to part 2 of this summing up stuff. What stuff? Exactly. Using the washer method. This is part 2 because this time, instead of revolving around a nice, friendly, horizontal x-axis, this time we're going to revolve around the line y equals -1/2. So, same setup as the first video. We have two functions, x squared and square root of x, and those two functions do have a bounded region right in here. We're going to take that bounded region, the region bounded by f of x and g of x, and we're going to revolve it around the line y equals -1/2. What that means is the line y equals -1/2 is the axis of revolution. It's the center of the revolution. And so you're going to get some three-dimensional object. There's going to be a lot of empty space in the middle of that object. And like with the washer method before, we don't want to count it in the volume. We want to find the volume of just the solid object formed when we do this revolution. And so in my picture here, I've tried to give you a sense of the stuff that we're going to sum up. We're going to sum up the volume of each and every one of those washers. Guess how many? Infinitely many. Guess how thin they are? Infinitesimally thin. The beauty of calculus. So let's do this. So we're going to find volume, and like we saw before in part 1, you should watch it if you need to, but in part 1 we saw that the volume of a washer is found by taking pi times what we called capital R squared times the height. And what we meant by that was, if you went from the center all the way to the edge of the entire washer, we call that the capital R, the big R radius. And then we subtract from that pi little r squared height. That is the volume of the hole. Now, pi r squared h is the volume of a cylinder. These are just really short cylinders. So we're taking the entire cylinder volume as if it was an entire cylinder and subtracting the cylinder, the hole in the middle that kind of got stamped out of our cylinder to get the volume of the washer. Now we made this look a little bit nicer. For instance, we factored out the h, so we had pi capital R squared minus pi lowercase r squared, all gets multiplied by h. Furthermore, we said that the height of these cylinders, I've tried to shade it in here, I hope you kind of see the three-dimensional nature of this, but the height of this cylinder is that little change in x. Now it's not just randomly, let's just put a dx on the end, why not? No, we're really thinking about that when we slice across that horizontal axis, the height of those cylinders is going to be that little itty-bitty change in x. And so all of this is going to be times dx. And I've left these blank because what about the radii? Well, we'll have to figure them out. I'm going to leave those blank for just a minute. But ideally, what we're going to do is we're going to sum up the volumes of all of those washers from 0 to 1. Still notice, this boundary is from 0 to 1. Check that out if you need to, but those two functions do intersect at 1, 1. So as x varies from 0 to 1, as x varies from 0 to 1. But what about those radii? Let's talk capital R here. The radius of the entire washer is the distance from the center of the washer to here. Now watch this, everybody. I want you to just think through this, like use your mind. Don't just memorize, but think through what's happening. Watch. How far is it from here to here? Now I stopped right at the horizontal x-axis here. So from -1/2 to the horizontal x-axis, that's a half a unit. Then from the x-axis all the way to the top, well, it depends. That distance is going to depend on where I draw my slice. Like, can you imagine, I'm going to do this one quick, but can you imagine I made a slice out here? Ooh. Now, it gets pretty ugly fast in terms of my art. We would have this washer out here, and this washer is going to have a radius from here to here, a half of a unit from here to here, but then, whoa, all the way up to there. Depending on x, that remaining distance could be greater or lesser depending on x. But notice that that height is just the function output from this square root of x function. For any input of x, we're going to output that f of x distance based on the square root of x. But it's 1/2 plus that function value. It's 1/2 plus that function value. So the capital R, let me give myself a little bit more room here, is the 1/2 from the x-axis to the axis of revolution was 1/2 a unit plus that additional or and that additional or is, depending on x, we have an output of g of x. Now, what about lowercase r, the radius of the hole? So again, the radius of the hole would have been from, we draw it in there again, I kind of got erased a little bit. So we're going from here to here, still 1/2, but then a little bit more. Still 1/2, but then a little bit more. And that little bit more, as we saw before in the washer method, depends on x. That little bit more could be little, or it could be more, or it could be more, depending on the input of x. But that output, that additional vertical height, is based on that function f of x equals x squared. So it's 1/2 plus a little bit more. It's 1/2 plus a little bit more. It's 1/2 plus a little bit more, and that little bit more is governed by the function f of x. I'm pausing there for a minute because you need to have a thought there. It's not about, but I thought it was negative 1/2. I know, but just look at the measurement. Think about how tall those things are. From that negative 1/2 up to the x-axis is 1/2 a unit. And then that little bit more. So it's 1/2 plus g of x, or 1/2 plus f of x to get that overall radius. So in terms of simplifying this, we have the integral from 0 to 1. We've got pi times, we've got that 1/2 plus g of x, and g of x was the square root of x. We've got pi, we've got 1 plus f of x, and f of x was x squared. Now let me come up over here. I would like it just to do one more step. Let's factor out the common factor of pi. So we have pi times the integral from 0 to 1. We have 1/2 plus the square root of x squared. We've got 1 plus x squared dx. Now, I'm going to ask you to pause the video now. And for this one, okay, I really want you to focus on getting this integral set up. Because here's the reality of the world that we live in. If you were doing something where you have to think this way, you need to set up the integral. Once the integral is set up, then you can put it into a Desmos, a Wolfram Alpha, or whatever software computer thing you got going on. The setting up of the integral, though, still requires all of this thinking and measuring and drawing and imagining. But then once the integral is set up, we do have technology. So let's be honest here in the year 2020. Let's go ahead and use our technology. Pause the video. I'm going to go get my technology because it's over there. And will you just put it into Desmos or whatever you want, and let's see what we get. I'm going to join you on this thing. I know you can't see it, but I'm going to go to Desmos, and I'm going to type in pi, and then I'm going to type in int, the integral from 0 to 1, and then I'm going to hit a parenthesis and say 1/2 plus the square root of x I hope you're doing it too, squared, and then minus 1 plus x squared dx, and Need some more parentheses on mine. What about yours? There we go. Look at that. Look at that. Hey, I'm not deleting this video because I've done too much, but where did that one come from? It's 1/2. Where'd that one come from? It's 1/2. Where'd that one come from? It is also 1/2. Yikes. Let me fix that. Oh my gosh, that is so much better. So this integral comes out to be approximately 1.989. Hey, let's just call it about 2 cubic units of volume produced when that region is revolved around the line y equals -1/2. Now next, we'll do a part 3. And in part 3, I won't make a mistake. And we will revolve around maybe like y equals 2 or something up there. That'll be fun. Go try some more problems. Think about this. Come back for video 3.